Hey, welcome back everybody to our statistics class notes. We're now on page 136, second page of section 9.1. So we're just diving in here to chapter 9, which is about inferring population means. And we're talking about right now the accuracy and bias of the sample mean. So for all populations, the sample mean, if based on a random sample, is unbiased when estimating the population mean. That means that we should assume our sample mean is doing a good job, as good a job as it possibly can, of estimating the true population mean. Now the standard error of the sample mean is defined as the following. So the standard error is equal to sigma, which is the true population standard deviation, divided by the square root of n. So we can see also here, similar to how we had n in the denominator of the standard error for the sample proportions, as the sample size increases, then the sample mean becomes more precise, right? So we get a standard error that gets smaller and smaller as the sample size increases. That means that the sample mean becomes more precise and clusters much more around the true population mean. Okay, so let's run through an example here. Let's say we have a student who has a large digital music library, and the mean length, the average length of the songs in the library is 258 seconds. So we're talking about the entire library of this student. So this is mu. This is the population mean of that student's library's digital library, music library, and how long all the songs are. With a standard deviation of 87 seconds, so that's sigma, the population standard deviation of the student's digital music library. The student creates a playlist then that consists of 30 randomly selected songs from her digital library. Okay, so I've already described it, but let's hammer it home. Is the mean value of 258 seconds a parameter or a statistic? And let's explain. So the mean value of 258 seconds of her entire music library is a parameter because it is the mean of the population, all songs in the digital library. We represent that mean as with mu, because it is a parameter, and that's the symbol we use for the population mean. Likewise, the standard deviation of 87 seconds is also a parameter because it is the standard deviation of the entire music library, all songs. So that is a parameter, and we represent it with the symbol sigma. Now, what should the student expect the average song length in her newly created playlist of 30 randomly selected songs to be? So she should expect that it's going to be really close to, right? She should go ahead and expect that it's going to be 258 seconds. The average length of her songs will be 258 seconds because the sample mean, x bar, is typically close to the population mean. It is an unbiased estimator, so that means it's typically close to the population mean. What is the standard error for the mean song length of the 30 randomly selected songs? And now the standard error of the mean song length for these 30 songs is going to be sigma divided by the square root of n. Okay, 87 divided by the square root of 30, which is 15.88 seconds. Remember, the standard error is the standard deviation of the sampling distribution. If I were to take repeated samples of 30 selected songs from the library, just take repeated samples of 30 and kept plotting their mean, and then looked at the standard deviation, that should come out to be 15.88 seconds, 87 divided by the square root of 30. If the student generated another random playlist that contained 50 songs, so now the sample size has gone up to 50, would this playlist have a standard error that is greater than or less than the standard error for her playlist of 30 songs? So remember, standard error, we're dividing by the square root of the sample size. So we have a fraction where n is in the denominator, and if n is getting bigger, that fraction will get smaller. Okay, so that means that the standard error should have a smaller, the standard error for the 50 song playlist should be smaller because the standard error decreases as the sample size increases, and you can see that from the formula.